In this video, we're going to briefly talk about the miscellaneous topics about the MOS transistors. First one we need to cover is what is the body effect. Again, use MOS as an example here. So essentially, usually, when we design a circuit, the source and the body voltage of MOS transistors is usually grounded. But in certain cases that actually, for example, in a cascade, the source voltage, with the MOS on top, the source voltage could be higher than the body voltage, right? The body voltage is sitting in the ground. The source voltage could be 0.2 or 0.3 volts above the ground. With that, actually, that can change the MOS threshold. This is very useful characteristics. So, actually, I often see two type of applications. One is people try to bias up the source voltage, bias the source voltage slightly higher than the body voltage to increase the MOS threshold, to actually decrease to reduce the leakage. Or on the other hand, what we can do is bias up the body voltage than the source voltage. So now the body voltage is slightly higher than source voltage. That, as you can guess, is decreasing the VT threshold. It's very, very useful in a lot of low voltage application. Second one is, how do we even know that the MOS transistor is in saturation? Right, as we said, most of the MOS in the analog circuit are in the saturation regions. But how do we know? Right, so there's many ways. Different designers have different ways to do it. But usually, one of those is by looking at the voltage across the VGS and the VDS. When you see a transistor with VDS slightly higher, VGS slightly higher than the MOS threshold, right, by 100 millivolts or 200 millivolts, while the VDS is more than, let's say, 200 millivolts and above, usually that MOS is in the saturation region. So that's one way to look at it. This way is, if you're using cadence or HSpice, you can print out the operating point of the MOS. You're gonna do a comparison between the GM and the GDS. If the MOS is in the saturation region, usually GM is tens of times or 100 times of GDS. So that's the second way to do it. I'm pretty sure that there are more than these two ways to do it, but probably more than enough for now. So one is to use MOS as a capacitor. Well, we're gonna explain this one in more details in the other video, but one thing to remember is, if you want a MOS cap, if you want to get an effective MOS cap, you need to use MOS as an example. You need to turn on the MOS, right? Essentially, put a positive voltage on the gate, reference to the channel source. So that's it. So one is the first one is the MOS diode. So MOS diode, you're gonna see this one in so many different places. You're gonna see the MOS diode used in the current mirrors, used in differential active load. Sometimes people use MOS diode as a voltage clamp. There's so many different places. Get familiar with this. You're gonna use it sooner or later. So MOS diode, VGS, of course, is VTH plus V overdrive, right? So, and also this VGS, usually you're gonna see this VGS drop across the temperature, right? When the temperature increases, the VGS decrease. And also, one thing to remember is the small signal resistance of this MOS diode is 1 over GM. What does that mean? So that means, for example, in this case, right? So we have 5 microamps pushed through the MOS, and the VGS is around 630 millivolts, with the sizing of W equal to 1 micrometer, L's the same size, right? Also 1 micro. So what if instead of using 5 microamps here, we're using 6 microamps, right? So that's 1 microamp change in the IDS. So the 1 microamps, so that's current, multiply this small resistance 1/GM. So that's equal to how much change you can see on the VGS, right? So let's say if you use 6 microamp here, the final VGS, large signal VGS, going to be equal to 630 millivolts plus this delta VGS here. Thank you for watching. If you like our video, please subscribe our channel.